This video is sponsored by Quiddy and their brand new Q2 3D printer. During the 1950s, the United States began developing these VTOL aircraft called tail-sitters, for the primary reason of having usable aircraft even when runways were destroyed by enemy forces. And most of these for the most part looked fairly normal, at least when compared to some other flying things. However, the French also decided to get on board with the tail-sitter idea and created something that sort of resembled a jet that got shoved into a barrel, called the Coleoptere. Although super goofy looking, I've always found its ring wing design to be really fascinating and something really cool to try out as a scaled down model, but I never really got around to it until now. Before I even had the idea of building a model of the Coleoptere, I was working on designing a single-copter, which is essentially a drone, but instead of directional control coming from motors and propellers, it comes from thrust vectoring vanes. The whole purpose of making this was to better understand PID values and also help me develop my own tail-sitter in the future, as this aircraft functions just like a tail-sitter in hovering mode. It came to me a while in the CAD process that it would be really sick to design and build a Coleoptere around the basic skeleton of a single-copter. Initially, I was a bit worried that adding a ring wing around a propeller would be terribly inefficient and steal a lot of the thrust the motor was producing. But after doing some research, apparently adding a duct around a propeller is supposed to increase static thrust in a hover and also increase flow stability. So I thought this project would be a good test of just that. As most of my projects do, this one started in CAD, and designing this airframe definitely came with some challenges. First being I had to modify the body since I was using a propeller instead of an EDF, which would have made more sense because the original aircraft was a jet. And secondly, trying to wrap my head around how I was going to fit the flight controller, battery, and all the other electronics in such a compact space. What I came up with was stacking the flight controller and battery with this table-like structure, and then somehow wrapping the stuff such as the ESC receiver and servo wires around. And then these walls running along the battery bay will help guide the fuselage onto the base of the body. For this build, I'm going to be using a variety of filaments such as PLA, lightweight PLA, and some carbon reinforced PETG, and they're all going to be printed on the brand new Q2 printer. I've had this printer for quite a while now, and it's definitely been super reliable and helpful for a multitude of projects. I've had the Quiddy XCF Pro for the longest time now, and the Q2 has been a big upgrade as it includes auto bed leveling, nozzle tip cleaning, fast printing, a compact design, and most importantly is super affordable for its 280 by 280 build volume, which is great for beginners getting into 3D printing. They sent me their carbon reinforced PETG, which will be great for a lot of the parts that will be supporting a lot of weight or stress. For the majority of the aircraft, I'm using this passive foamed lightweight PLA, not only because it can be up to 40 to 50% lighter than normal PLA, but also because it just so happens to be the right color. Now for the flight controller, I made a big mistake by using the SpeedyBee F405, because in the future I ended up with a lot of reliability issues. And also for these types of VTOL aircraft that require precise servo control, it makes a lot more sense to use a higher processing flight controller like a H7 board. But I just ended up using this one because I had it on hand. For the firmware, I'm flashing iNav, which is relatively new to me since I mainly use ArcticPilot. But doing custom servo mixing is a lot easier in iNav, and ArcticPilot is really only necessary if I want to do some complex waypoint missions, which I'm not going to be doing in this project. After that, I began printing all the various parts and gluing them together using some Gorilla Superglue and some thin CA. It was a bit tricky to figure out how to embed the servos into the ring wing, but I found the places where the four fins were had perfect spots for some servo pockets. And bloop. Oh man, that looks pretty cool. And for the central hub part that will hold all the electronics and connect the body to the wing, I'm printing one half in lightweight PLA and one half in the carbon reinforced PETG for some extra strength. This green part is what will hold onto the motor and hold the table-like structure for the battery and flight controller. Looking back, this motor was definitely not powerful enough, but at the same time it was kind of dumb to make such an experimental design fully 3D printed, because it's just going to be really heavy. But that's just what happens when looks are favored over function. For the landing gear legs, I'm using these 4mm carbon fiber rods that are secured with some Gorilla Glue. The glue expands while curing, so it helps to lock in the legs so that they don't fall out. This turned out looking a whole lot better than I was expecting. Sick. I do like the orange. It does add a little bit of difference in the color scheme, but man, looks so cool. The flight controller then needed some iNav configuration for the servo mixing, and then after that the central hub could be put together. Both the table structure and the battery bay are printed in the carbon reinforced PETG, and you can see here how the fuselage will slide along the guiding walls of the battery bay. For the ESC, I'm using this little BL Heli 45 amp that just barely fits in the little pocket around the flight controller. Here goes the battery bay getting screwed on with some M2 screws, and the fins were attached using some super glue and these control rods, so the fins could still rotate independently while supporting each other. So after a whole lot of cable management the nose does fit on, which is honestly like, I did have to make that slight cut there just so then that those pins can reach out, but like it is incredible that everything can actually fit in here. And if I do take off the nose, look at that. It's a whole lot of wires. Initially, I tried to test it on the carpet, which ultimately didn't work because I was raising the throttle too gradually, leading the aircraft to always have an urge to tilt to one side. To fix this, I put down a wooden plate as a base so the aircraft could move around without tipping over. But I was still too scared to throttle up any faster, so I only got a few legs off the ground at first. And after some flights and pit tuning, the whole aircraft was definitely feeling more stable and not wandering all over the place. For the people wondering what I'm actually doing to get this thing to stay relatively stable in the air, I'm adjusting these tuning parameters called PID values, which stands for proportional, integral, and derivative. PID values are used for many different applications, but for our case it determines how the fins will react and account for errors based on movements detected by the flight controller. The proportional gain determines how aggressive at which the flight controller wants to move the servos to correct unwanted movement. For example, if the proportional gain is too high, it will cause oscillations. Too low, and the aircraft will be sluggish to respond to errors. The integral or I term accumulates errors over time and applies a correction to eliminate persistent offsets such as wind or off-center weight. It helps to prevent long-term drift by correcting errors that do not go away on their own while the aircraft is in the air. If the I term is too high, it can cause low-frequency oscillations and overshooting. And finally, the derivative or D term acts like a dampener, smoothing out sudden movements and helping to prevent overshoot. Now, to speak quite truthfully, trying to visualize those parameters in action for this specific project is actually pretty difficult to do, and that's why it was also really difficult to tune this thing properly. Well, looks like that's the end of that. To hopefully prevent damage from future crashes, I began testing the aircraft while it was hung by a string, which ultimately didn't work that well because if it went too high, the string would get caught in the propeller, and if it went too far away, it would just get yanked back by the string. It was also during this time I was getting a bit fishy on whether some of the issues were from the flight controller or the PID values, because there were certain moments where I didn't change the PID values and the flight controller just began freaking out, and it was just not working the same as it used to be. One of the biggest issues I had with this project was simply the inconsistency of how the aircraft would behave at times. Sometimes it would work really well, and then the next day, without changing any of the parameters, it would just not work at all, which makes it nearly impossible to tune the aircraft properly. I'm not completely sure, but my suspicion is that something with the flight controller's accelerometer got messed up, but I couldn't really try different flight controllers since that would require me to reprint everything. Another thing I found interesting was that the aircraft was a lot more unstable and uncontrollable once the nose was added back on later, which didn't make much sense to me since the nose was so light that I didn't think it would have that great of an impact. Okay, so these are the new PID gains. We're trying to lower integral, higher D term, lower P term. It was at this point that it seemed like any change I made to the PID gains or other parameters had no effect on the actual aircraft, and I almost felt like I was going full circle because the aircraft was experiencing a lot of the issues I had in the past. I tried reattaching the nose, and surprisingly after that it did seem to be more stable and more controllable, even without adjusting the PID gains afterwards. But of course all that was out the window when the next day I went to go test it. It flew completely differently than it had before. we are actually getting somewhere. I am really happy. It's really interesting. I need to go back and figure it out, like what happened, because these, like, the PID gains I just loaded in were just the original PID gains from when it worked the best. Using those previous PID gains, it works so much better. Like, it can take off the grass really well, and it can actually land. Unfortunately, this was the point of the project where it was hard to make very much future progress. Once again, after it worked really well one day, it returns back to not working and crashing. There were some moments where it began to work again, but ultimately it never mattered because it would always just go back to being uncontrollable the next day. Reaching to this point of the project was definitely really frustrating because it's a problem that most likely relates to the flight controller itself rather than the actual tuning. However, this is definitely not the end to the Coleoptere project because I do plan to come back and focus on the functionality aspect and ability to do both hover and forward flight. Although this project wasn't the exact outcome I wanted, I definitely think it could work by using some different hardware and some small tweaks. So I have the Onshape document linked down in the description so you can adjust the model to fit your electronics and give a go at getting it to work better than I did. Or you can just print it and have it as a small scale model. But anyways, that's it for this video, and I'll see you later. Bye.